Whenever you are.
Hi. Hey guys!
Hey!
It's just your friendly Toy Story buddies, Buzz and
Woody.
Woody.
Just,
you know,
doing our thing.
Yeah, we're hanging out with some toys here, of course.
Mm-hmm.
So, and we're going to talk about the trends in the periodic table.
Yeah.
So, you've learned about the periodic table, and it's got groups, and it's got periods, but, you know, why is it all the way it is? It's like, we could do a philosophy class, too.
Yes. Yes, it is, yes.
Yes. So, here we go. Let's take a look.
Wait,
Okay.
Okay.
We'll just do this way. All right. Hey, there it is.
You didn't turn it on.
It's not on. How do I turn it on, buddy? Okay, and here we go. All right. So, periodic trends. What is a trend? Just a repeating pattern.
Okay.
Okay.
Sure.
Like, what's trending? Like, you know, like when you look on the internet and you find out what people are wearing. What's a cool thing to do? That's a trend.
Like the Twitter?
Yeah, the Twitter.
Things that trend.
The things that trend on the Twitter. Yes,
Gotcha.
yes.
Okay.
So, and what we're looking at when we look at the periodic table, it's just repeating patterns of physical and chemical properties.
Okay. Sure.
So in this case, we're going to look at 3 major trends, and we're going to look at how they change as you move across the periodic table and down. Okay? So here we go.
Okay, I'm ready.
Okay, so the first one that we're going to talk about is ionization energy.
Oh, good.
Okay, big crazy word, ionizing. Whoa. Okay? And really what it is just the amount of energy needed to remove your valence electrons.
Oh, so wait, ionization energy is the energy to turn it into an ion?
Absolutely.
Oh, well that's nice and easy.
Yeah, it's super simple.
Cool.
Okay? So, if you have a lot of high ionization energy, it's because you're holding onto your electrons really, really tight. Like, you don't want to let them go.
Gotcha.
Okay? And remember, we're talking about our valence electrons. So, when you're talking about high ionization energy, I have helium on here because helium's valence electrons are right outside the nucleus. So, they're, like, gripping onto those bad boys. Like,
really
never
tight.
letting
Very
you go.
Close. Gotcha. Okay.
Okay? So
that would have really high ionization energy.
Absolutely, yes.
Gotcha. Okay.
Okay, and then really low ionization energy means you're going to give up your electrons very easily.
Okay, so big atoms?
Big atoms are more likely to give up their electrons.
Okay,
yes.
I gotcha.
Okay. So, and of course, I don't know, I have a random dot, but the one that has the greatest amount is going to be ionization energy. So, an easy way for you to think of that is, as you have helium in that upper right-hand corner on your periodic table, okay, and you're looking at it, the further you get away from it, the less ionization energy you're going to have.
Gotcha. So then, francium, way down there,
would have
the least.
Correct.
Gotcha. Okay, that makes sense.
So here's a little, maybe like a little more of an analogies to help you remember what ionization energy is. Okay?
Ooh.
Here I am, Teacher Barbie, with my stacks of money, because as a teacher I make buttloads of cash.
Yes, I know.
Mm-hmm. Yes. And there you are, the robber.
Yes, I'm very sneaky.
Yes. Okay, so, for example, if my money is stored in my purse right next to me, it's going to take you, the robber, a lot of energy to try to get them away from me.
Yeah, it's going to be harder for me to steal it if you're, like, clutching onto your money.
Right, exactly.
Like helium with its electrons.
Exactly.
Gotcha, okay.
So, but say I store my stacks of cash out in the middle of the football field.
Yeah.
Okay, a stupid move, we all know that.
Exactly.
But if, say I was Teacher Barbie, and I said, I'm just going to leave this couple million just chilling in the middle of the football field. Okay, because my money is much further away from me, then you can just walk up and say, see ya.
Gotcha. Or like students with cell phones, right? It's harder to take someone's cell phone if they're holding it versus they leave it on their locker and go to class.
Exactly.
Gotcha. Okay.
Okay, so that's how I remember ionization energy.
That's fun.
Okay, so here's our example of ionization energy. Up there in the top right-hand corner is helium, so it's the darkest.
Oh, look at that.
Okay, so as you move across the periodic table from left to right, just like we read, okay, it is going to increase.
Yes.
Okay, because our valence electrons are staying on when we're looking at a period, they stay on the same energy level. Okay, so they are more tightly held.
There you go. Yeah.
Okay, and as we move down, now we extend our atom. It gets larger by adding an energy level.
And then that's your money being farther
and farther away.
Gotcha. Okay.
Yeah. So make sure you notice the trend for here. So increase going across.
Yep.
Decrease going down.
Yeah.
Okay. Then we move on. Atomic radius. What do you think atomic radius would mean?
Ooh, I'm going to assume it has to do something with like radii or size.
Absolutely. Okay, so this is the distance from the nucleus to its outermost. I'm sorry. I know I'm very. I'm
much
buzzed.
wider.
Yes. Yeah. Okay. So it is the distance from the center all the way out to the valence electron.
Okay. So just how big the atom is.
How big the atom is, okay? So there's a little picture there for you showing you these different sizes of the atoms, okay? And as you see, as you go down, obviously, the atoms get bigger because every time we go down a group, we're adding another energy level.
Okay.
Okay? So, for our atomic radius now, it is the opposite of our ionization energy as far as the trend goes. I increase going down because as I go down, I'm going down and adding an energy level every time I move a period down.
Gotcha.
Okay? And as I go across, I am decreasing. Okay? I know it's a little crazy,
it's a little
but
weird because I'm adding protons.
You are adding protons, but think of that as like your magnet's getting stronger.
Oh.
So it's actually pulling those electrons in tighter.
I gotcha.
So your atom's not really like shrinking per se, but it's just getting a little.
So the nucleus is getting bigger, but the nucleus is really small. It's the cloud that's being pulled in. Gotcha.
Yes.
Okay, I see what you're saying.
Yeah. So increase down for atomic radius, decrease across.
And it's opposite of ionization energy.
Absolutely.
Because they're completely opposite things, right?
Yep.
Big atoms lose electrons easily. Okay, gotcha.
Okay. And then the last one we have is electronegativity.
Ooh, that's a big word.
It is. But it's like electric.
Oogie, oogie, oogie now?
Yes. Yeah, okay, we're there.
Yeah.
All right, that was a reference you guys probably won't.
No.
Anyway,
your parents will.
Yes. Electronegativity is the attractiveness, as I like to say, of the element. Okay? So the atom's sexiness, if you will. Yeah, I know it's kind of weird.
Well, yeah.
But we're talking about how likely an atom is to gain another electron.
So the opposite of ionization energy.
Right. Yes.
So ionization energy is losing electrons. Electronegativity is pulling them in.
Exactly.
Okay.
So they're going to pull them closer to themselves because they are going to want to bond with an atom.
Okay.
All right.
Yeah. Like especially nonmetals, right?
Right.
Nonmetals will want to pull in and share in those electrons. Okay.
Okay. And our most electronegative element is fluorine. It wants that one extra electron so badly.
Okay. And is that because fluorine is the smallest non-noble gas?
Exactly.
Oh, okay.
Yes, because noble gases have 8 valence electrons, so they don't bond with anybody. They're like loners, the cool people.
Yeah.
Okay. And then group 17 is the ones that only want 1. But since fluorine has only 2 energy levels, its valence electrons are not that far. And it just wants that one so bad to be the happiest element on the planet.
Yeah.
Okay?
Yeah.
So everybody wants to bond with fluorine.
It's a really sad story. Fluorine is so close to being happy.
It is.
But it's not.
Exactly. Okay. So how bad an element wants an electron. Okay. All right. So here we go here. Okay. And now this, as you will notice, is very similar to what trend, Mr. Wood? Do you remember?
I would say this is going to be very similar to my ionization energy trend.
Absolutely.
Look at that. Ooh,
boy. Because I'm decreasing as I go down, which is the same thing for ionization energy, and I'm increasing as I go across the period.
Okay.
Okay.
So they're measuring opposite things, but in opposite ways, right?
Exactly.
Ionization energy is how much energy you need, and electronegativity is how much they want.
Exactly.
So it's measuring it in a different opposite scale.
Exactly. It's a little confusing.
A little bit, but that's okay.
Yeah, we'll get you there. Okay, and all we're focusing is on the trends. Can you remember which is going which way?
I can.
Okay.
Yes.
So, well, we're going to head back and play with the toys, because that's what we do as Buzz and Woody.
Yep.
So, we'll check you in class.
Okay.
See ya.
Bye.